Okay, hello everyone. I'm Nian from Shanghai Jiao Tong University. Today, I'd like to share our latest work about designing a scalable lock for the asymmetric multi-core processors. So the single ISA asymmetrical processors, which is also known as the big little cores, combine several faster high-performance big cores and several energy efficiency little cores to achieve better flexibility in various workloads. Such an architecture has become more and more popular in mobile and desktop processors, even on some edge servers. For example, most mobile processors like the ARM Big Little architecture or the dynamic architectures are all AMPs. And the desktop processors like Apple M1 and Intel's 12th generation Alder Lake processors are also AMPs. So in such an architecture, the system scheduler, like the energy-aware scheduler in the Linux kernel, are free to place any threads across symmetric cores. Multi-threaded applications may need to synchronize among asymmetric cores to achieve better peak performance. Thus, scalable synchronization primitives under such an architecture are highly needed as before. However, we find that all existing scalable locks fail to scale in AMP. Here we present a result of a micro benchmark to showcase the performance collapses encountered by two representative locks in AMP, including the MCS lock, which represents the locks that preserve the acquisition fairness, and the test and set lock, which represents the unfair lock. The micro benchmark keeps acquiring the same lock over and over again and adding to a global counter in the critical section. We measured the average throughput and the lock acquisition latency on Apple M1, which contains 4 big cores and 4 little cores. The x-axis shows the number of lock competitors, which are bound to different cores in Apple M1. The first 4 threads are bound to different big cores, while the others are bound to different little cores. As shown in the figure, when we scale from the big cores to little cores, both the throughput and the latency encounters an obvious collapse. After an in-depth analysis, we find that the root cause is that all existing locks implicitly assume symmetric cores. However, in AMP, their assumption no longer holds, which leads to collapses in throughput or latency, or even both. To be more specific, firstly, in AMP, the computing capacity is asymmetric. Thus, it will take the longer time in little cores to execute the same critical sections. For example, here we showcase an execution timeline of 2 big core and 2 little core system. The green box represents the time of executing the critical sections. Obviously, the little cores have a significantly longer green box. However, therefore, for locks which preserve the acquisition fairness and give the little cores an equal chance as the big cores to execute the critical sections, the overall throughput will be hurt. So what about the unfair lock? Unfortunately, they also encounter scalability problem in AMP systems. Besides the computing capacity, we also find that the success rate of the atomic operation is also asymmetric. Thus, unfair lock, which relies on the atomic operation to decide the lock holder, suffers significantly skew in the chance of holding the lock. So when the big cores have a higher chance to win the atomic operation, little cores can barely lock, which brings latency collapses, even starvation. Fortunately, big cores have higher chance to lock, which result in executing more critical sections and thus higher throughput. We observe such a tendency in most ARM platforms. However, in some other platforms, for example, the Apple M1, we find that the little cores sometimes have a higher chance to win the atomic operations. Thus, the throughput will collapse due to that most critical sections will be executed on the slower little cores, and the latency will also collapse since the big cores can barely lock. Although the scalable locking has been extensively studied over the decades, all of them cannot scale in AMP. Firstly, those work does not consider the asymmetric between cores, and most of them targets NUMA or many-core systems. Thus, their techniques either reducing the cross-node memory references in NUMA or reduce the lock contention in the many-core system do not take effect in AMP. Second, all of them rely on the long-term fairness to forbid the long latency or even starvations, which give the little cores the same opportunity to lock in a period and will bring the same throughput collapses as the fair lock, like the MCS lock, as we have just analyzed. Even though existing locks fail to scale in AMP, we can draw several implications from their behaviors. First, their acquisition fairness is no longer suitable for AMP. So why existing locks still lead acquisition fairness? We find that they preserve the fairness to ensure a low or limited lock acquisition latency and forbid starvation. Since such a fairness brings collapses in AMP, we should design a new lock ordering specifically for AMP to achieve scalable throughput as well as satisfying the latency target. Second, the unfair lock like the test and set lock implicitly reordering and prioritizing big cores and achieve higher throughput when the big cores have higher chance to win the atomic operation. However, the unbounded reordering also brings extremely long and unpredictable latency to the little cores. Thus, if we want to achieve scalable throughput in AMP, reordering is indispensable. However, it must be bounded to prevent extremely long lock acquisition latency in little cores. To solve the lock scalability problem in AMP, we propose a new latency-guided lock ordering. Upon FIFO order, such an ordering reorders big cores with the little cores as much as possible to prioritize big cores for better throughput under the condition that the little cores will not violate the application's latency requirements. For examples, there are 5 competitors on the slides, A, B, C, D, E. And A, C, E are from the big cores, and B, D are from the little cores. Currently, they are all in a FIFO order. In the new latency-guided ordering, since B's latency is far from exceeding the requirements and it is from the little cores, C from big cores is allowed to reorder with B and lock first. However, since D's latency is going to exceed its requirements, E cannot reorder with D to preserve D's latency. To implement such an ordering, we provide a new lock library, libSL. libSL adopts a multi-level design. The bottom level of the libSL is a reorderable lock, which exposes the bounded reorder capability as a reorder time window upon existing FIFO lock. It provides 2 new interfaces to acquire the lock. The first interface, lock immediately, behaves exactly the same as the original lock procedure of the underlist FIFO lock. It directly enqueues the lock competitor to the lock waiting queue. The second interface, lock reorder, take another argument, the window. Such a window represents the time that the lock competitors could wait considering its latency requirements and allow others to reorder before it. As shown on the figure, when calling the lock reorder, the lock competitor will not enqueue directly, and it will become a standby competitor. It will also set an alarm which rings when the reorder window expires. When there are other competitors called lock immediately during the reorder window, they can reorder with the current competitors and enqueue first. When the reorder window expires and alarm rings, the competitors will enqueue the FIFO waiting queue so that no more reorder is allowed. There also is a special case when the queue is empty. The standby competitors will directly hold the lock by occasionally check the queue status to forbid wasting the CPU time. By doing so, we can expose the bounded reorder capability as a controllable reorder window. However, the reorder window is per lock acquisition and is fine-grained. In the real world, the latency requirement of application is always coarse-grained. For example, the application may have latency requirements of the whole request handling procedure in the right code block, which may contain several lock acquisitions. Thus, there exists a huge semantic gaps between the coarse-grained application's latency requirements and the fine-grained reorder time window. And it is hard to set the reorder window directly according to the coarse-grained latency requirements. To bridge such semantic gap, libSL first collects the application's coarse-grained latency requirements through easy-to-use interfaces in the form of a latency SLO, and use a runtime feedback mechanism to map it into fine-grained reorder time window. Specifically, libSL regards the code blocks which has latency requirements as an epoch. And the epoch is coarse-grained, which means it can contain multiple locks, branches, or even nested locking. For example, the whole request handling procedure on the figure is an epoch. Each epoch has a unique ID, and the libSL collects its latency requirements in the form of latency SLO. SLO is the service level objective. For example, epoch may have SLO of 1 microsecond, which means the P99 latency of the epoch is supposed to be 1 microsecond. Developers have to use epoch start and epoch end to wrap the latency critical code blocks, mark its unique ID and its latency SLO, which is also the only required human effort to use libSL. When executing the applications, libSL will transparently redirect the pthread mutex lock to suitable interfaces of the reorderable lock. Specifically, if running on a big core, it will call lock immediately, which allows them to reorder with the standby little core competitors. And the competitors from the little core will then call local reorder. The reorder window is per epoch and mapped from the latency SLO. All local acquisition in that epoch will use that window. For example, when calling pthread mutex lock from little cores in the 5th epoch, libSL will query the 5th epoch's metadata and set the reorder window accordingly. The reorder window is mapped from the latency SLO using a feedback mechanism. Since the reorder window has a similar effect of adding a short delay before each acquisition, the window size has a monotonous relationship with the epoch latency as shown on the right figure. Thus, libSL can adjust the reorder window at each epoch end according to the latency of the current epoch. If it exceeds the SLO, it will shrink the window. Otherwise, the libSL will enlarge the window. To be more specific, we adjust the window in an additive increase, multiplicative decrease, conservative manner. Once the epoch exceeds the SLO, we directly shrink the window by half, like the green point on the figure, so that the epoch latency is expected not to violate the SLO next time. If the latency SLO is defining the P99 latency, we will divide the reduced window into 100 slices and enlarge the window only 1 unit each time. In such a way, the next lightning executions are also expected not to violate the SLO, and the 100 execution will have a similar latency as the one before shrinking the window. It will triggering the next window shrink, where our P99 latency is successfully maintained. In real world, the execution process and the contention level of the lock may vary over time. Thus, the epoch's lengths can be heterogeneous, so that the relationship between the reorder window and epoch's latency may also vary. However, by adopting such an AIMD conservative control algorithm, libSL can still precisely maintain the tail latency even when epoch's lengths become heterogeneous. We present the effectiveness of the feedback mechanism through a micro-benchmark result. It records the latency of every epoch in big cores, which is a purple line, or the little cores, which is a green line, during the first 350 milliseconds. We change the epoch's lengths at a different point and set the SLO to 100 microseconds. For example, we enlarge the epochs by 128 times by visiting more shared cache lines in critical sections at 100 millisecond point and shrinks back to original lengths at 200 millisecond point. As shown in the figure, the AIMD algorithm can precisely maintain the latency under the SLO, even when the epoch's lengths change rapidly and randomly during the 250 milliseconds to the 300 milliseconds. When the epoch is too long so that SLO is impossible to maintain at 300 milliseconds, libSL falls back to FIFO so that big cores and the little cores will have a similar tail latency, And we evaluate libSL on Apple M1, which has 4 big cores and 4 little cores. When the big core is about 3.75 times faster than the little cores, with the help of a core name team, we run an unmodified Linux on Apple M1. We evaluate libSL in various applications, including 5 real-world databases. We first present the results from a micro benchmark. In this benchmark, all threads rapidly execute the same epoch, which contains multiple critical sections of different lengths protected by different locks. In each critical section, thread will read, modify, write a specific number of shared cache lines and execute a specific number of loop instructions between two lock acquisitions. We present epochs tail latency in little cores, big cores, and overall separately. We set the SLO of libSL to different values shown on the slides, where the max represents the default maximum reorder window in libSL to maximize the throughput without causing starvation. As shown on the figure, when we set the SLO to 0, libSL behaves similar to the MCS lock. It is because that the SLO is impossible to achieve, and the libSL falls back to FIFO. Compared with the test and set lock, when achieve a similar throughput by setting the SLO to 25 microseconds, libSL reduces the tail latency by 50%. And when having a similar latency by setting the SLO to 50 microseconds, libSL improves the throughput by also 50%, which can further go to 1.2 times when setting a larger SLO. Compared with MCS lock and P-thread mutex lock, libSL can improve the throughput by up to 1.7 times and 4 times. We also compare libSL with the Shuffle lock, which is a lock reordering framework that can only take static reordering policies. libSL's latency-guided ordering is not static, thus cannot be easily adopted into Shuffle lock. Instead, we adopt a static proportional-based policy in the Shuffle lock by giving the big cores a fixed 10 times higher chance to lock. Such policy will introduce unpredictable latency and throughput so that a fixed proportion regarding different latency requirements of different applications is difficult to set. Besides precisely maintaining a given latency SLO, libSL outperforms the Shuffle lock by 70% when having similar latency. It is because that libSL has a better cache locality by batching more big cores before passing it to little cores for low SLO violation, which is only possible in libSL because it's fine-grained timing control on each lock competitors. At last, we compare libSL with the optimal policy, which directly chooses a static window without a window adjustment to present libSL's performance headroom. When having a similar latency, the cost of the window adjustment is only 6%. Thus, libSL can achieve close to ideal performance the latency allowed. We also present the scalability figure, which uses the same configuration with our motivation cases. As shown in the figure, when we set the SLO to 12 microseconds, which is the same as the test and set lock, it can bring better scalability. If we further enlarge the SLO to 50 microseconds, the throughput barely drops when scaling to little cores, and the latency is precisely maintained. We further present the evaluation results from the Kyoto Cabinet benchmark. Kyoto Cabinet is an open source in-memory key value store. In each epoch, the threads will have 50% chance to put a key and 50% chance to get a key, so that the epoch's lengths are heterogeneous. A similar result can be observed. When setting the SLO to 0, libSL behaves similar to the MCS lock. When achieve a similar throughput as the test and set lock by setting the SLO to 70 microseconds, libSL reduces the tail latency by over 90%. With a larger SLO, libSL can improve the throughput by up to 23%. When compared with the test and set lock, which goes to 95% when compared with the MCS lock and the P-thread mutex lock. We also show how libSL performs under different SLO settings. As shown in the left figure, when setting a larger SLO along with the x-axis, the tail latency of epoch executed in little cores sticks strictly with the y equals x line, which means libSL allows big cores to reorder as much as possible so that little cores can barely meet their SLO. The throughput, however, grows gradually with a larger SLO as the red line. We also present the latency CDF of the epochs executed in little cores and overall separately. As shown in the figure, a clear boundary can be seen in the overall latency since most operations are executed on the big cores. Due to the intensive contention, only a small part of the requests are executed on the little cores, and thus has a longer latency. There is also a clear boundary in the little cores latency. About half of the operations have a shorter latency due to the shorter execution time of the get operation. As for the longer put operation, since the reorder window grows linearly when the latency exists the SLO, the probability also grows linearly after the half SLO. We conclude the performance of the libSL in all benchmarks through a latency throughput figure. The red line represents the throughput of the libSL with different SLO settings. The fail MCS log has the lowest latency, yet the lowest throughput, which is a green triangle on the figure. Compared with it, libSL can trade some useless latency, which is still under the SLO with significant better throughput. Compared with the unfair log, like the test and set log, when it shows big cost affinity, which means the big costs have a higher chance to win the atomic operation. It has better throughput, yet higher latency. Compared with it, libSL can have better throughput when having similar latency and a lower latency when achieving similar throughput. Moreover, unlike the test and set log that is only an unpredictable point on the latency throughput figure, libSL can achieve close to ideal throughput the SLO allows. For example, when the SLO is very strict, libSL can meet the SLO target, while the test and set log cannot. Otherwise, when the SLO is relatively loose, libSL can have a far better throughput than the test and set log. When the test and set log shows little core affinity, which means the little core has a higher chance to grab the log, libSL always performs better than it. To conclude, we present the first asymmetry-aware scalable log, libSL. To provide good scalability on AMP, libSL adopts a new latency-guided AMP-aware log ordering. libSL adopts a multi-level design. The bottom level is a reorderable log, which exposes the bounded reorder capabilities through reorder time window. And the libSL maps applications coarse-grained SLO to the fine-grained time window through feedback mechanism. Evaluations on the real-world databases on real desktop AMP, the Apple M1, shows up to 5 times improvement. That's all for today's talk, and I'd like to take questions.